Hello. In this video, we are going to cover trigonometric functions and their integrals. I'm not going to do everything that is covered in the book, some of which is rather elaborate. I just want you to know a few basic integrals of trig functions that are a little bit beyond what you may have at your fingertips now. And then we'll see some examples of how we can extend that to get others that you won't be expected to memorize, but we might need for other things. Right, so just file away. Knowing how to do integrals of trigonometric functions could be very useful to me as I move forward. So basically, here's the goal. Sine, cosine, tangent, secant. We want to be able to integrate those functions and their squares and their cubes. But if we can know all 12 of those, that's a good basis for our necessity with these as we move forward. And I'm just going to tell you, cosecant and cotangent just aren't as important. Almost anything we want to do, we can achieve with sine, cosine, tangent, and secant. Okay, so hit pause, and for these 6 things that I have here, fill out as much as you can. Okay, so sine squared plus cosine squared, there is an identity that says that is always equal to 1. My hope is that you just plain know this. And not just that you know it, but that you're on the lookout for it. That if I have an expression with sine squared of theta, or an expression with cosine squared of theta, I can rewrite them using this. But that's what's really important, because sometimes you won't be told to use this identity. You just need to realize it's in play. If there's a sine squared, you'd rather it look like a cosine squared. And then this one, maybe you don't have memorized. I will tell you, tangent squared of theta is 1 plus 1 equals secant squared of theta. And what you can do, if you don't have this just plain memorized, basically you can take the identity we just talked about that hopefully you do know, and if you divide everything by cosine squared theta, you'll notice that's what we have here. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. You don't have to have this one memorized if you just want to recover it whenever you need it. What you do want to realize, of course, is the same idea. That expressions with a tangent squared and expressions with a secant squared, we can rewrite them, perhaps, to make one more convenient than the other. Remember that fact, and then you can probably recover how do I use the identity. Okay, a couple of integrals that we should just plain know. So this one is negative cosine. Oh, not a d theta plus c. This one is sine theta plus c. This one, either you recognize it or you don't, but you should know that that's tan theta. And then this one here is technically a u substitution, but hopefully you can kind of do that in your head and realize, oh, okay, if I had sine theta to the 6th power, I would get 6 times sine theta to the 5th power, and then chain rule gives me that cosine. So that's what's going on here. If we have a bunch of sines and just one cosine left over to kind of cancel with chain rule, that's great, or vice versa. So you should know these integrals. And for this last one, you should be comfortable with anything that sort of reminds us of that. It doesn't necessarily have to be a 5th power. Right, so there's an expectation you know all of this stuff. And then there are 2 more that I want you to know. They may not be things you think you already know. So take a moment and try to figure out what would be the antiderivative of tangent squared and what would be the antiderivative of tangent. And the hint is try to rewrite them. So hopefully you remember, we just said tangent squared plus 1 is equal to secant squared, which means that tangent squared is secant squared minus 1. And we know the antiderivative of secant squared is tangent. We know the antiderivative of 1 is theta, and there we go. So this one's quite easy if you just remember to make a substitution. Just have that in the back of your mind. Tangent squared and secant squared, we can substitute one for the other. Same with sine squared and cosine squared. And now here, if we just use the definition, this is sine over cosine. And we'll notice that the numerator is basically the derivative of the denominator. You could do this formally as a u substitution. But what if we just took natural log of the absolute value of cosine theta? The derivative of that would give us 1 over cosine theta. Right, I'm just sort of thinking over here. I prime would be 1 over cosine theta. Then by chain rule, I multiply by negative sine theta. And that's pretty much what we have except for the minus. And a way some people write this to avoid the negative is they move that negative inside as a power. Right? This is not inverse cosine. This is cosine theta to the negative 1. And that's secant. So this version you may see more often, but this one is fine as well. Do you want to have this memorized? It's really up to you. If you simply remember that you can integrate tangent by writing it as sine over cosine and doing u substitution with natural log, you can recover it pretty quickly. Okay, everything that follows is not something I expect you to have memorized, but we're going to see some applications of using integral facts and integral techniques we already know to figure out new ones. And again, maybe just having a list of these will be helpful as we do other problems. The next section sort of hinges on being good at trig integrals. And here being good maybe just means we can look up the ones we need to know. So here's an identity you may or may not have seen before. If I double an angle and want to know its cosine, it's cosine squared of the original angle minus sine squared of the original angle. So this is just an identity. In a perfect world, you know this, but I'm just handing it to you. But here's what I want you to do. First, rewrite the right side by replacing sine squared theta. And also rewrite the, rewrite the right side by replacing cosine squared theta. So it's not really the right side that's important, but what are we substituting? Right? Sine squared and cosine squared, we can substitute them for each other. Write both versions. I'll hit pause and try this. Okay, so for this first version, I would have cosine of 2 theta equals cosine squared theta minus, and I know sine squared theta is 1 minus cosine squared theta. So if I distribute my negative in group-like terms, here I have 2 times cosine squared theta minus 1. Now let me try something similar over here. Cosine of 2 theta equals cosine squared, which I'm writing as 1 minus sine squared, minus sine squared. So that's 1 minus 2 sine squared theta. Right? These are equal to each other, but they look kind of backwards. Now, if I use this one on the left, I can solve for cosine squared. Do that. So I have cosine of 2 theta equals 2 cosine squared theta minus 1. I'm just recopying. I can add 1 to each side. And then I can divide by 2. And I'm actually going to switch the order over here just so that it's completely unambiguous that the constant 1/2 is not part of the cosine. Sometimes it's kind of optional. People will put that argument in parentheses so that it's clear that nothing else is part of the cosine. And we can do something similar over here. We would have cosine of 2 theta is 1 minus 2 sine squared theta. So negative 1 plus cosine 2 theta equals negative 2 sine squared theta. Divide everything by negative 2. And I have sine squared theta equals, equals positive 1/2. Sorry, let me write this better. Divide everything by negative 2. So I have 1/2 minus 1/2 cosine 2 theta. equals sine squared theta. You might notice if we add these together, we'll just reconfirm that cosine squared plus sine squared equals 1 because the other part cancels. So what we've done here is we've rewritten sine squared and cosine squared in terms of things that are much easier to integrate. So integral of cosine squared theta, well, that is the integral of 1/2 plus 1/2 cosine 2 theta. Integral of 1/2 is 1/2 theta. Integral of cosine 2 theta, well, that would involve a sine 2 theta. There's already a 1/2 there, and then there's a 2 we would need to cancel from the chain rule. So it would look like that. Right, let's just double check. If we take the derivative of this, we get cosine of 2 theta times 2. 1/4 times 2 gives us the 1/2. And then we have a similar one here, just with a minus. So we would have 1/2 theta minus 1/4 sine 2 theta cos theta. You do not have to have these memorized, but you want to know that these are things that are well known, and we can look them up if necessary. Okay, this next one involves a trick, and I'm not expecting you to memorize how the trick works. It's just a very clever little thing. Suppose we want to know the integral of secant. If you write it as 1 over cosine theta, there's really no substitution that will be helpful. So although this is true, rewriting it is not helpful. Let's keep calling it secant. So now here is the trick that kind of comes out of nowhere. What if I just multiply top and bottom by secant theta plus tan theta? So I'm creating a fraction. Obviously, top and bottom, I've multiplied by the same thing. It's still equal to secant theta. Then I will distribute in the top. So in the top, I have secant squared theta plus secant theta tan theta. Then I'm doing a really clever thing here. And when I say I'm doing a clever thing, I am repeating a cleverness that was discovered by someone else. I'm just switching the order of those two terms at the top. So I have secant theta tan theta plus secant squared, all over secant theta tan theta. So maybe this is obvious, maybe it isn't obvious, but look at the relationship between top and bottom. If y is equal to secant theta plus tan theta, the derivative of that, well, the derivative of secant theta is secant theta tan theta. Derivative of tan theta is secant squared theta, and that's exactly what we have in our numerator. So we actually have an example where we have a fraction where the numerator is the derivative of the denominator. So what we have here is natural log of secant theta plus tan theta, plus c, obviously. Because if we took the derivative of that, this goes in the denominator, and then we multiply by the derivative of the inside. So not one you need to have memorized, but someone has figured this out. Right, so we're making pretty good progress. Here's another one with a substitution that is not obvious. If I want to know tangent cubed of theta, so what I'm going to do here is I'm going to write this as tangent theta times tangent squared theta, which I can substitute. Tangent squared theta is the same as secant squared theta minus 1. Now I'm going to distribute. So I have tangent times secant squared theta. So that's 1 tangent and 2 secants. I have that over here. I've written it in a different order for reasons that will become clear later. But hopefully you realize tangent theta times secant squared theta is what this is. And then the other part is tangent of theta times 1, which is tangent theta. So here, this thing in parentheses is the derivative of this thing. So we can actually treat this as like u substitution, where u equals secant theta. What we actually have is secant theta squared. If I take the derivative of that, I want to cancel that 2. But the derivative of this, the 2 comes in front, and then I would have secant theta, then by the chain rule times the derivative of secant theta. There it is. And then Integral of tangent, let's just look that up. We know we figured it out before. Integral of tangent is minus natural log of cosine theta. Oh, I don't need that plus C, sorry. Okay, sorry, I'm goofing here in terms of my integrals. A little distracted. I'm doing this outside because there was no empty space otherwise. So this is 1/2 secant squared theta, right? We're not taking an integral anymore. And this would be minus the natural log of the absolute value of cosine theta. So one way of simplifying this would be like so. Something you can look up if you need it. All right, just a couple more. So what about sine cubed, right? We have tangent cubed. The ones we haven't addressed are sine cubed, cosine cubed, and secant cubed. So here's my hint, right? I want you to try the first step. If we're trying to integrate that, do it with integration by parts. Now, obviously, what we're integrating here is just sine theta times sine theta times sine theta, right? And I want you to ask yourself, how many copies of sine theta are easily integrable? Right? I don't mean possibly integrable, but easily integrable, and make that your dv. So pause and at least try the first step. So my hope is that you realized integrating one copy of sine theta is very straightforward. Integrating more than one copy of sine theta involves one of these tricks. So let's suppose that u is sine squared theta and dv is sine theta d theta. So we're separating. Two of the sine thetas go in u, the other one goes in dv. So du would be 2 sine theta cos theta d theta. V is the integral here, which is negative cosine theta. So when we make our substitutions, we have the integral of u. Sorry, we have u times v minus the integral of v du. Okay, so let's clean this up. Here I'm just going to move my negative to the front. Here I will notice I have a double negative, so that's plus, coefficient is 2, and I have cosine squared theta sine theta. Let's notice, here I have cosine squared, here I basically have the derivative of cosine squared. So this is u substitution, hopefully you can do it in your head. This part stays the same. And now here, if I had cosine cubed of theta, I took the derivative of that, the 3 would come in front and I'd have 3 copies of it. I don't want 3, I want 2, so I have to multiply by 2/3. Then by the chain rule, the derivative of the inner function, the derivative of cosine, would be negative sine. I have positive sine, so let's just fix that negative. So this is one version of the answer. Now I'm going to do a little switch just to present it in a way that perhaps seems more elegant, and then we'll see a symmetry with the other one. So I'm going to make another substitution. I'm going to notice that here I have cosine, here I have cosine, here I have sine squared. Let's substitute the sine squared, because I know that sine squared is actually the same as 1 minus cosine squared. And so it's kind of nice here, I'm setting this up so that it's just in terms of cosine. We're doing an integral of sine cubed theta, and we're getting an answer that's just in terms of cosine. So what does this look like? When we distribute everything here, we would have negative cosine theta. If we distribute again, we would have plus cosine cubed theta minus 2/3 cosine cubed theta plus c. So one version of this would be negative cosine theta plus 1/3 cosine cubed theta plus c. And again, that was our antiderivative for sine cubed. You do not have to memorize this. I want you to appreciate that we can get it just by integration by parts and things we already know. And then a very similar argument shows that the antiderivative of cosine cubed is sine theta minus 1/3 sine cubed theta. Okay. We'll notice that it's really just the opposite cofunction. If we integrate or differentiate opposite cofunctions, we'll get opposite cofunctions. So a very similar pattern. I'm not going to go through it. All right, one more. Let's do integration by parts on secant cubed theta. So again, ask yourself, how many copies of secant are easily integrable? Hit pause and at least try the first step. Okay, so I'm going to say u is equal to 1 copy of secant, and then dv is secant squared d theta. Because secant squared has an easy integral, right? Let's put 2 copies of secant into dv. So du would be secant theta, tangent theta, d theta. That's our derivative there. And then if I integrate here, I get tangent theta. So when I do my u substitution, this is equal to u times v minus the integral of v du. So v is tangent theta, du is secant theta, tan theta. Okay, so I'm going to rewrite all this, and I'm going to rewrite the whole equation. So integral of secant cubed theta, d theta, equals secant theta tan theta minus tangent squared theta secant theta. And this is where we're going to do another substitution. I'm going to take this occurrence of tan squared and rewrite it in terms of secant squared. I'm choosing to rewrite the whole equation for reasons that may become a little more obvious in a moment. Tangent squared theta is the same as secant squared theta minus 1. So I have secant cubed theta d theta equals secant theta tan theta minus secant cubed theta after I distribute minus secant theta. So I have secant cubed, integral of secant cubed theta d theta equals secant theta tan theta minus, I'm going to break these up, integral of secant cubed theta, and then here I have plus integral of secant theta d theta. Now, what we're going to notice is we have secant cubed theta on both sides. It may feel like our integration by parts has failed, but actually we can group the like terms, right? They're not canceling. In fact, we can move one to the other side. So we would have 2 copies of integral of secant cubed theta d theta equals secant theta tan theta plus integral of secant theta we covered before. You can look that up. It is 1/2 times the natural log of secant theta plus tan theta. Absolute value in there. So now we can just divide by 2. No one said this was fast. No one said this was easy. No one said this was fun. Oh, I actually got ahead of myself by putting that 1/2 there. Right? I knew it was coming. Right? No one said this was easy. No one said this was fast. No one said it was fun, but it's possible. And if we really need to know some of these things in an analytic way, so many of them have been figured out by someone in the past. Right? There are a lot of tricks that lead to this. We don't have to come up with all the tricks ourselves. We just need to appreciate that this is possible. So if we go back to the beginning here, if you check through all these notes, you will realize that all 12 of these, either you already knew them or we have addressed them. Okay, that's it.